This is, let me say, a very basic lecture on radiation detection and protection in a laboratory. It's like introduction of the laboratory session. All right, I show you some slides about the fundamental things of radiation detection. I will go through some relevant things on radiation detectors, operation principles, and some words about radiation protection in the lab. All right, perhaps I will, so that you can see, I will be here. So, you can see, can you see? You can see, all right. So, as you can see, there are different types of radiations. These are limited, of course. There are a lot of other types, but these are main objects in this course: alpha decay, beta decay, and gamma emission. So now you have to understand what's the difference between ionizing radiation and radioactive material. And it is possible that emission during the decay, it's possible that emission of charged and neutral particles are possible. Neutral particles are, of course, X-rays or photons in general, or neutrons in some cases. But as I told you, there are several other types of emissions. So, this is the basis of all radiation detection, which is based on the interaction between medium, the detector in fact, and the radiation itself. So, let's assume that this is a detector, this one, or some kind of material, alphas, betas, gammas, neutrons, and other radiation. They behave different in a different way in different materials. So charged particles interact strongly and ionize directly. So do you know what's ionization? It means that the radiation kicks out electrons from the electron shell. So neutral particles interact less, and they typically penetrate farther to the detectors. So there are different mechanisms: ionization, excitation. Also, they produce heat, and there are some other mechanisms too. So, if the detection principle is interaction between the radiation and the detector, how we get the result out? So, we must have some kind of signal, and the signal is electric signal, like this one. But the signal is very weak, very, very weak. So it has to be amplified, usually in and practically always in two stages. There is a pre-amplifier in your detector, which is very close to the detector material itself. Then this signal is again amplified, and then finally, after some manipulation of the signal, we can have a, in this case, we can have a counting signal. So as you know, this is very familiar to you, but alphas do not penetrate. Even paper stops alphas. But gammas, and especially neutrons, they go deep into the material. Betas go, for example, 1 centimeter around. It depends on the beta energy. So, when you are monitoring environmental radiation, you practically have to do sampling. In some cases, it's not feasible, but usually you do sampling. Sometimes radioactive materials are present as discrete sources, as in this case. I think these are some industrially used materials. But sampling is often necessary in environmental cases. You can take samples from soil, from a surface, wipe sampling, from water, for example, and in this case, from a test tube and from air. This is an air sample, very small one. Okay, let's go through about detectors. So, different types of ionizing radiation detectors are used in radiation protection and also measurements in the environment. There are gas field detectors, scintillation detectors, semiconductor detectors, a lot of other type of detectors. And the choice depends on different things, which are, for example, where the radioactive material is located. Is it external or internal radiation with respect of your body? For example, in this case, they are measuring thyroid. Do you know what are the radio elements that are in your thyroid in a nuclear incident? Iodine, yeah. And iodine 131 is the most valuable, if I can say this way, valuable nuclide. So the selection of the detector also depends on the environmental conditions. For example, in this case, something is measured. I don't remember anymore what is detected here, but there is snow outside. So in Finland, this is especially important because in the winter time it's cold there. Sometimes you have to measure contamination, and this is typical in laboratory conditions, because you have to follow that you don't disperse radioactive material all around. So yeah, you have to check the contamination of the lab. How often do you, in this laboratory, how often do you check the contamination levels? In this lab, yeah.
Every 1 month we use a handheld dosimeter.
Yeah, all right.
To check the
All right.
And in our radiation gamma chamber, there is a device outside.
Yeah.
So gamma radiation chamber, we checks every day,
Yeah.
like every second.
All right. Yeah. Okay. Then the choice of the detector depends, of course, on the radiation type. So in this case, they are measuring alpha radiation from an air filter. This is counter, not a spectrometer, this one. We can measure gamma radiation from the ground, beta radiation from a surface, or neutrons in different conditions. And finally, if you have to select between a counter and a spectrometer, in case of a spectrometer, you get out a spectrum. However, in case of a counter, you just put all the signals together, but you cannot identify the nuclides by using a counter in normal cases. All right. Then there are other type of detectors like these ones that should be used in some laboratories, not in not generally in environmental laboratories because the dose levels are quite low very often. But in nuclear facilities, you have to use these kind of detectors. All right. Then there are some other things that influence the choice of the detectors. So one limitation is that what is the energy window or energy areas that you have to detect. So it depends on the thickness of the entrance window. Sensitivity of the detector is very relevant in some cases. If the radiation field is very high, for example in nuclear reactors, then this sensitivity is not necessarily the biggest, or how to say it, it's not necessarily important, but in environmental conditions when the radiation fields are quite low, then it's good to have a sensitive detector. One point is that is the detector appropriate for high contrast? Normal spectrometers, the count rate should not be too high. It depends on the size of the detector there. So there is so-called dead time. So if the dead time is too big, then you get out nonsense. One thing regarding the choice of the detector is this. Is it battery driven or how the detector is cooled? Then these are the things that are very important when you have to do measurements in the field. Size, weight. You cannot use these gamma ray spectrometers in this fixed laboratory outside of this building. You need a truck. But in the field you have to carry things. So robustness is one thing, easiness of operation, etc. Okay, let's have a quick look about the operation principles of the detectors. So, let's start with gas-filled detectors. So, this is a detector, this one, and there is gas inside. There is an electric field between the surfaces. What happens when ionizing radiation comes to the detector? It can come here from left or from the top or from the bottom, but positive ions, electrons are generated, and using voltage between the cathode and anode, we get the signal out. These so-called gas-filled detectors, they are classified in different, different type of detectors. There are ion chambers, proportional counting chambers, and Geiger chambers or detectors or counters. So it depends on the strength of the electric field. So in this area we can in fact have we can identify energy of the radiation. These are not very good in terms of resolution, but we can identify the energy. However, if the voltage is high, typically 1 kilovolt or something like that, each photon, beta, alpha, or whatever coming to your detector generate a signal which is dispersed all over in the counter, and you get out signal, but you cannot identify the nuclide. All right. Regarding ionization chambers, typical gases are air, argon with methane, etc. They are using quite low voltage. So signal amplitude is proportional to radiation energy. They apply quite well for gamma and X-ray measurements. So number of generated ion pairs, they are proportional to the gas mass and density. And you get more efficiency if you use high pressure gases in the chamber. There are some examples of small ionization chambers here, and also alarm systems, they use ionization chamber. Proportional chambers, they are like these ionization chambers, but they use intermediate voltage. So there is an electron multiplication, because in these cases it may happen that because the voltage is not very high, the generated ions and electrons might combine together inside the chamber, so there is no signal. However, in these cases, there is an electron multiplication which is proportional to the original number of ion pairs. So it's possible to obtain energy spectrum of the radiation. So, in fact, we can measure alpha particles or low energy photons if the source is placed in the filling gas. And this is Geiger counter. I already explained that there is an electron avalanche which is not depending on the original number of ion pairs. All right. And as you can see, there are a lot of different types of Geiger counters. The point for these is that they are very simple to use. They are usually calibrated on the dose rates. For the energies quite close to cesium-137. Advantages are they are robust, simple electronics, low price, sensitive, and it is possible to connect alpha or beta probes together here.
Sir, Sir, all these Geiger counters can be used as a contamination monitor?
Yes, they can be. Not all of these, but some of them. It depends on the detector. Yeah.
Portable gamma radiation monitors, PRS.
Yeah, I think yes.
It is attached to GM counter.
Yeah.
GM cube actually. So can we please use as a contamination monitor? It's a portable one.
There is I think they have a separate system.
Yeah.
So it's like a screen. I mean, this part of the detector present. So they are not necessarily Geiger counters, those contamination monitors. It depends on the case. And then there are scintillation detectors which operates so that radiation coming here or from the bottom They generate photons inside here. Then there is so-called photocathode that makes this signal to release an electron, which is multiplied here, and we get signal out. These are the connector pins here. There are scintillation detectors here. So the electron pulse is proportional to the energy of the original radiation. So these are in fact spectrometers. There are a lot of different types of scintillation materials. There are organic, inorganic materials. There are also solid and liquid materials. These are the typical materials. Perhaps this is the most common material. And the good thing is that the density is high, which means also quite good efficiency of the detector. In this picture, we are testing lanthanum bromide detector, and I think this is sodium iodine, this is lanthanum bromide. This is a pressurized ionization chamber. But if you are using these type of detectors in environmental measurements, I mean outside laboratory, the problem is that they are sensitive for temperature changes, which makes energy calibration, it's not necessarily valid in different temperatures. And lanthanum bromide detectors, which are quite modern, they have quite good energy resolution, but there is intrinsic background coming from this nuclide. All right, now you can see spectra from different type of detectors. In the bottom, green ones, this is sodium iodine detector. I guess that the source was cesium-137, it's this energy, and cobalt-60 here. And this is, I think, yttrium-88. I guess so. Now you can see the resolution, I mean energy resolution. Energy goes in this axis. Number of counts goes this axis. As you can see, in case of lanthanum bromide detector, the resolution is quite good compared to this sodium iodine. However, high purity germaniums, they will give us very, very narrow peaks, which makes possible to distinguish peaks which are located very close. For example, these two peaks here, you cannot resolve them by using especially sodium iodine detector. So, typical density of high purity germanium, it's around 5. Same is for lanthanum bromide and sodium iodine, it's a little bit lower. But the point is that interaction strength is better when we have a dense detector. Interaction probability is higher compared to air. Do you know the density difference between air and, for example, water? There is a difference between 1,000, which means also that for the radiation point of view, it interacts strongly with dense material. Okay, there are some other things that I will not explain just now here. You can read these things afterwards. So, solid scintillation detectors, they are appropriate for gamma spectrometry. And liquid scintillation detectors, they are for alpha and beta spectrometry. But you have to mix the sample to the scintillation material. This means that usually the sample should be in liquid form, but not always. This is the comparison between sodium iodine and lanthanum bromide spectrum in case of iridium source. So the difference is not very big, but anyway there is some difference. Some years ago we tested how to use unmanned aerial vehicles like this one in environmental monitoring. We put a sampler here. We put a small spectrometer, this one, to the fuselage of the UAV. Before doing that, we compared resolution of different type of detectors. Here is a cadmium zinc telluride detector. Here is lanthanum bromide, sodium iodine, and calcium iodide detector. In fact, the best one today, I think it's a cadmium zinc telluride. But as you can see, in case of calcium iodine detector, the resolution is not very good. All right, then I tested also this very small detector. The size is some centimeters only. And we tested it because we intended to put this detector in this UAV, but we didn't do it. So you can see the resolution, which is quite good. For example, in these peaks, there is not very much overlapping. But a question. So, are there any reasons to mount, for example, this kind of small spectrometer in a drone? Do you have any ideas? Of course, it must be a small detector because the drone is very small, this one. I think the size is like this one. Do you have any idea? Okay, if you are looking for example, nuclear fallout, and these kind of vehicles, they don't go close to the ground. They stay quite up, 100 meters around. Then, if the detector is small, you cannot detect practically anything. However, in case of a nuclear accident or incident, when the radiation level is high and there is radioactive material in air, then it's an advantage to have a small detector because dead time may be quite large in case of a large detector. All right. So these spectra are from the EU 252. The source is located here. This is the sodium iodine, lanthanum bromide detector, and this is this CHROMEC detector, very small one. Mass is very small. Now we got the point. Alpha and gamma spectrometry. You can see alpha alpha detectors, not spectrometers. Detectors here, they are more or less spectrometers here. These are germanium detectors with different shapes. There are cooling system here, the detectors are here. There are different type of systems. These are electrically cooled here. So the operation principle is more or less same as for the ionization chamber, but instead of mobile ions, radiation produces free electrons and holes in the semiconductor material. And they are around 10,000 times more sensible than gas-filled detectors of the same size. And because of the higher density. They can be applied in alpha, beta, gamma, and X-ray spectrometry, depending on the energy of these and the radiation type, of course. So, typical semiconductor materials are silicon and germanium. They are doped with impurities to create either N-type or so-called P-type conductivity. So, ionizing radiation, which are traveling through the detector material, produce free electrons and holes. I will consider these interactions in later presentations, but the generated electrons, they are transferred from the valence band to so-called conduction band. They can move there, and an equal number of holes and ions, electrons are created. They are collected and separated by using internal electric field. Electrons move toward the anode and holes toward the cathode. So, the number of electron-hole pairs is proportional to the energy absorbed into the semiconductor. A pulse is generated whose magnitude is proportional to the energy deposited by the radiation. In the left you can see a typical alpha spectrum, and in the right typical gamma ray spectrum. So, do you have any comments why they are so different? Of course, energies are different. You can see that the typical alpha particle energies are quite close to 4 up to 9 MeV. Typical gammas are quite close to 0 up to around 3 MeV in case of natural radiant lights. So there are differences in the spectra, and these depend on the radiation characteristics, how they behave in the detector. The peaks are more or less same, but there is a difference between the background. Do you have any comments on this? Okay, if not. So, in case of photons, you have to remember that the energy is always the same for each photon. For example, for cesium-137, it emits exactly 662 kiloelectron volt photons. However, in the detector, the signal is different because of some things that I will explain later. And according to some of my previous slides, the endpoint is spectrum, gamma ray spectrum. Peaks are relevant. These are not relevant here. They disturb the analysis, in fact, but we have to take them into account in the spectrum analysis process. These things will be explained later in the laboratory and also in next lectures. So, what are the differences between silicon and germanium? So you can see the charge number is by a factor of 2. There are some heavy or dense materials also. I haven't tested this kind of detectors. Never. You can look at these things later, but this is a typical alpha spectrometer. I mean high resolution alpha spectrometer. And, there is this part of the detector is sensitive for radiation, and thickness is around this size, sub-millimeter size. So, do you think is it good to have thicker alpha detector? Who says? Yeah. Can you explain why? Yeah. Yes. That is one point. That is one point. Did you hear that? So, one point is also if the detector is thick, then it can detect also gammas, X-rays, and other particles, which makes difficult the analysis. That's why it was optimized to be very, very thin. Regarding gamma detectors, there are different types of detectors. What kind of detectors you have here? In STUC we have these planar or thick planar detectors. We have also one well detector, mostly P-type of detectors.
We have one N-type and two P-type.
One planar and two P.
Yeah, one
Yeah.
N-type and two P.
All right.
What is a P-type coaxial? What is a P-type coaxial?
Hmm?
P-type coaxial.
Yeah.
Like we have.
No, you have. All right. We have also this kind of well detector. So you can put your sample, which is generally a test tube. Basically, if this detector is very large, you can put this inside the detector. But what I have found is that there is a problem of coincidence particles, and it is very difficult to take into account in case of well detector. I will explain this later, but okay, these are good detectors, of course, because of what? Because of the high efficiency. Because all the radiation, if the beaker is in the bottom of a well detector, so practically all gammas are detected. However, in case of planar detectors, most of the gammas are coming out of the detector. So the terminology is geometrical detection efficiency. It's high in this case, not very high in these cases. However, these are very good detectors in general. All right, then there are a lot of different detectors. For example, films or imaging plates, they are very useful. In this case, I remember that it was almost 30 years ago when I did autoradiography. I got a sample from one of our nuclear reactors, and one of my colleagues wanted me to analyze that sample. And the purpose was to check that how radioactive materials are dispersed in the filter. So you can see that each of these black spherical areas, they shows the location of so-called hot particles. So it's now I forgot the concept, but it's quite non-homogeneous case. Usually it is assumed that your samples or whatever you are measuring, they are assumed to be homogeneous. Okay, some slides about radiation protection in the laboratory. Please take these things into account. So you have to stay away from active sources. You should use shields when the source is active, and it's a good way to keep some distance. You know this thing already. So in some cases you might need these in environmental monitoring, but this is for the nuclear accident. Normally you do not use these kind of things. However, in case of a laboratory, you might need these ones. Do you have any idea what's the source here?
What kind of source is being used? Alpha, beta, or gamma?
What is your suggestion?
Yeah, answer. How many of you say alpha? One. How many you say beta?
I mean, I don't know the source, but it's not useful for gammas, at least high energy gammas. For in the case of X-rays, this might be good, but for betas, this is perfect. And especially if this is plastic, why not glass? It is because of so-called bremsstrahlung. Because if the electrons stops very quickly, bremsstrahlung, it's a very difficult word. It's coming out from the shield, and it generates, of course, doses. So it should be plastic or something like that. All right. I think this is one of the latest slides. So when you are working in the laboratory, you have to know the doses that you receive from radiation, and effective dose is the main quantity that is important. Also, equivalent dose is important. And they depend on the radiation type, energy of the radiation, and type of tissue. And effective dose is the weighted sum of organ-specific equivalent doses, and the unit is sievert. It is calculated like that, very simple. But in fact, very complicated to determine, basically. All right, and different quantities are needed to characterize the doses. There are several other type of doses, and especially this effective dose. This one cannot be directly measured. However, we can have an impression of the dose by using, for example, Geiger counter, which is well, basically not calibrated to the effective dose. However, you have to do sampling to evaluate these parts. However, you cannot do sampling from your colon or lung or liver. It's not possible, of course. Maybe afterwards. Okay. Okay, this is it. I hope that this is okay in the beginning of the laboratory session, and this is only, as I told you, very brief introduction. Okay, thank you very much. I don't have. I don't have questions.
You said in accident conditions, small detectors.
Sorry, because of this noise, I want to go closer. Yeah.
You said in accident conditions, if there is an accident condition, small
Yeah.
detectors are preferable. Can you explain to it as why we are requiring small detectors?
Yes. It depends on the.
Kind of radionuclide or
Yes, but also if you compare the detector sizes,
okay.
and if the radiation feed is very strong, you get too many signals to your detector. Especially spectrometers might be non-useful in those cases if the signal level is too high. Then it's better to have a small detector. However, detectors like here, they are good for detecting environmental radiation, because the signal, the amount of signal or density of the signal, it's so low that they are very good for that. But you cannot put high energy, high actively source close to the detector. It is so-called dead time. Is it? Do you think is this okay? All right. Any questions? Okay, but if there are no questions, you can ask me later. So
Yeah.
it's,
Yeah. So, no more questions? We go to the lab. We see the various equipment. So definitely we will be spending 2 hours in the lab to see the facilities, and tomorrow onwards we start it. And if you finish today early, then we may start to do it. That's what, yeah. So you should see that also. So try to spend as much time as possible, and there is no afternoon, evening, there is no limitations. You can be there in the lab up to 9 o'clock. If you want to interact with our scholars, try to learn, so, because we are here around the clock. Okay? So we have shared the group details already. So accordingly, batch 1 and batch 2 go to gamma spectrometry. So today we'll make one thing, because they want to go to radon bandwidth. Batch 1 will go to gamma spectrometry, batch 2 will go to alpha spectrometry, batch 3 will go to radon. Batch 3. Okay?
Alpha spectrometry and gamma spectrometry, like radon is on the top.
Right.
So group 3.
And when you finish, we have